Prompt engineering, at least the manual kind, it's a trap. It's a ticking time bomb waiting to explode in every single LLM application ever written. And I'm not just here to make claims in thin air. I'm going to show you 2 different ways that your prompts are guaranteed to backfire. But don't worry, I won't leave you hanging. I'm going to show you a different paradigm, something I found with DSPy that eliminates the need of prompt engineering entirely, or at least it gives it a whole new meaning. So let's start with the problems first. Okay, so for today, we're going to work with a task management application, which usually takes in user statements like I bought my groceries or I want to add a new task. And then it identifies the intent of the user, like what does the user actually want to do, and it will then go ahead and get those tasks or add those tasks or mark them as done. So the first step in our pipeline is going to be some kind of an intent classifier. Now here I am using BAML. Nothing against BAML. I still love BAML a lot. I mean, you could be using anything, right? The point is you're writing some kind of prompts. Like even if you're using L, even if you're using an agentic framework, it doesn't matter which framework you're using. Every framework kind of forces you to write a prompt. Well, it does matter if you're using LangChain. Please don't use LangChain. Just don't. Okay, my bad. Oh, sorry, you didn't see this. Ignore this part. It was never here. Okay, so you have a prompt, and for the classifier, we have a very simple prompt here. Identify the user's intended action based on the provided query. Just ignore this part. I'll show you that later. And then in the user message, we just provide the query directly. Now, if I open this up, this is how the actual query looks like. Like in the system message, we have that main instruction. We're also defining that, okay, the answer should be in JSON, and it should be either add task, get task, delete task, or mark task as done or unknown. Yeah, there are 5 things here. And my user query goes right here. I bought my groceries. So I bought my groceries. That action is fairly straightforward. It says that the user has completed an action. So it's mostly supposed to be marking a task as done. Now, we don't really care if that buying a grocery is a task present in the database at this stage. All we care about is identifying the user's intent first. Okay, so let's run this query. And by the way, I'm using Gemma 3 12 billion. And the answer we get back is marking a task as done. Perfect. That's exactly what we wanted. So it's looking good so far. But let's say something new happens. Let's say Gemma 3 is kind of expensive and maybe kind of slow as well. Our boss figured out that, oh, Microsoft has another model called 5.4, and maybe that would be a cheaper and faster alternative. So what do? You kind of replace it, right? We have to listen to our boss sometimes. We just have to. Okay, so it's 5.4. You know what? It's a good enough model, same range. It should work as well, I guess, perhaps. So let's run this. And what does 5.4 give us back? Add task. That's what it gives us back. So we just saw that changing the model sometimes breaks our prompts. And that's completely natural. Every new model is going to have their own prompting guides. And I know this is a fairly naive example. However, even if you extrapolate it into something bigger, the problem remains the same. Different models are going to read instructions and pay attention to different aspects. And it's very much possible that changing your model may fail things. And this is a big hit. Like, what if 5.4 or a newer model which comes out is like half the cost? And we're seeing that all the time. So you know what? It's fine. We'll bite the bullet. We'll stick with Gemma. It's fine. Go Google, whatever. So something new happens in our lonely application right here. We find a query which we've not seen before. I don't need groceries. So the user is not trying to mark a task as done. Instead, the user is trying to say that, hey, I don't need this task anymore, so perhaps we should delete it. So let's try to run this instead. Again, we're just using Gemma. There we go. And unknown. It kind of fails. And that's understandable. Like, we don't want our model to get every novel use case right every single time, especially because this is like a whole different use case which we just discovered. That's fine. We can forgive it. So what do we do next? We actually have to go back to prompting or prompt engineering, whatever we call it these days. Okay, so let me revert back the prompt and add this instruction back. So what we're doing, we're essentially just providing some instructions. Now, there could be different ways to do it. I'm just putting it as markdown. But the idea is that, hey, use the delete as action whenever you think the user does not need or care about a task anymore, which makes sense, right? Again, not the best prompt engineering example, but it doesn't matter. Just extrapolate this in real life. I'm sure you faced this before. Now, let's run the test again. We're working with I don't need groceries. Let's run it. And it works. Perfect. that's how it should be as well. But what about the previous one? What will happen if I run that again? Oops. It was supposed to be mark task is done. So if the query was, I bought my groceries, we want a mark task is done. So the second problem we just saw is that whenever we tune our instructions for the newer use cases that we discover, it often breaks the existing ones. Now, I am absolutely sure that you guys have your evaluations and your eval sets, and you're going to catch this before it reaches production. But that's not the point I'm trying to make. The point I'm trying to make is you have to go back to the drawing board and keep prompting till you get all those evals right, or a big percentage of them right. That's just a lot of time wasted. I mean, at this point, can we even call it prompt engineering? It's more like prompt fiddling. And we've all been there, right? Like your prompts end up like this spaghetti mess of instructions, of schema, of few short examples of these weird prompting engineering techniques that we are seeing on guides and on YouTube videos. Things like, hey, if you don't do this right, I'm going to kill the world. I'll give you $10,000. You have absolutely no idea how many of my unborn children have I had to sacrifice just to get a JSON output right. It is absolutely insane. Okay. And I've heard like so many prompt engineering stories. You know what? Share yours in the comments. Just let me know, what is your crazy prompt engineering story? Something crazy that you've done, which you have no idea why it works, but it works and you're too scared to touch it now. Let me know in the comments below. So the real question still remains. You can fix broken prompts. I know you can. You can engineer your way or prompt engineer your way out of it. You can spend the next 3 hours micro-fiddling and making sure the instructions are just right. The real question we need to ponder upon is, should you? This is the trap. You feel like you're making progress when you're doing this prompt fiddling exercise, but you're actually building on a very unstable foundation. As soon as there's a different model or there's a different use case, this house of cards that we are erecting, it's going to collapse. What we want right now is to stop thinking of prompts as something we write ourselves. We need something better. So I think it's time to bring out our favorite tool, Excalidraw. So this is like the old way we used to do things, right? And obviously, like even for this task management app, we have some kind of workflow in our mind, right? We start with the classifier, then we'll go ahead and actually call those tools and stuff like that. So you have some kind of workflow in mind. And in those workflows, you'll have like different areas where you want to use LLMs to get tasks done. In our case, the intent classifier. So once you have a task, what do? We immediately start fiddling with prompts. If you've experienced this enough, you probably even have some eval sets on day one. But the point is you're still going to write some prompts. You're going to try to write some instructions and make sure your evals pass, right? So you fiddle with those prompts, you manually test them, and some might work, some might not work. So kind of breaks all the time. So you might just keep doing this. It's like a iterative cycle, and eventually you will get it right. And I know you will absolutely get it right. But as soon as you have a new update, like a new use case or a new model, what do? You go back to prompt fiddling, and you have to do this entire exercise again because it will break and you will have to refiddle, and and the problem here is actually that writing prompts is almost like writing assembly instructions directly for your chipset. Like you're writing code directly for the Intel processor. So tomorrow, if a better processor, even from Intel or maybe another company comes along, you'll have to start writing those assembly code all over again. We don't want to do that. We don't want to work with such a low level abstraction. We want to work with something a little bit more high level, something more human readable, something more declarative. Like we just want to describe our tasks and let the system figure out the prompts for us. We want the prompts to be a byproduct. That's where the DSPy Way comes in. If you relate with this crazy loop of pain, just, hit the like button. It really helps me. And it's a very easy way to let me know that, hey, I'm making videos, I'm making content which resonates with you. So I'd appreciate that. So how does this compiler idea actually works? Well, that's where DSPy comes in. So the initial part is still the same. You still have to identify like your workflow. You still need to know what task you need the LLM to do. I mean, you still need to know that, hey, we want an intent classifier. That's what we want. So let's just start with that for now. So what DSPy technically does is that instead of forcing you to write prompts, it's going to introduce two new concepts, the signatures and the modules. So the first thing we do is create a signature. What is a signature? It's not a prompt. You're declaring or you're defining the desired behavior for that LLM task. So instead of writing individual instructions like, hey, if you get this kind of input, say delete task. Or instead of using prompting techniques like, hey, think before you answer. So what you're going to say is the user is going to give you a statement. And as the output, I want one of these 5 classes. That's it. So given a user's request, give me back the intent. So it's just a declarative contract without any implementation detail. In fact, we're not even going to describe how many LLM calls are we going to do to get this done. No implementation details. It's just the contract. So the next logical question is definitely going to be, how do we actually implement this task? How do we actually implement this contract? That's where the concept of a module comes in. A module is a strategy to get the task done. Again, it's not the prompt. You're not writing the prompt here. You're just deciding what strategy do you want. So what is a strategy? Well, the most simple or the most basic strategy could be, hey, take this input, just pass it to the LLM and get the output back. That's it. It's just an LLM call. Just do that, right? That's what we call the predict module. That's the most fundamental module we have in DSPy, right? Sometimes just giving inputs to the LLM directly and getting back an answer is not enough. We want something more complex. So what if we add a step-by-step thinking process to it? Like, hey, before answering, just think before you answer. That's your chain of thought module. And it doesn't even have to be a single LLM call. You could actually implement an entire workflow or a full-fledged agentic strategy with tools. The point is, the definition of the task and how you implement the task are 2 different things. And this is very important because this means that I can have different strategies to implement the same task and see which one works best for me and gives me the best results without having to rewire or rewrite my entire program. So now that we're not writing prompts ourselves, what are we doing instead? And how is the compiler figuring out the optimized prompt for us, right? How does it know that the prompt works or not? This is the key paradigm shift in DSPy, right? We're going to shift our attention from writing prompts to writing evaluations. So an evaluation is nothing but, getting some example data. So it could be generated, it could be curated from production. It doesn't matter. So you have like sample inputs with sample outputs, right? And then you write a function, which is called a metric, which will check whether the module's generated output is the same as the expected or desired output. So in our case, it's just going to be a simple function which checks whether the action matches. The action generated by the module and the action generated in the example, are they matching or not? That's pretty much it. That's the only cue the optimizer needs to actually create the optimized prompt. Now, don't worry. I know this is way too complicated. We're going to see a concrete example in code just to crystallize all of this. It's just important to understand the mental model. And it's really important to understand that we are not going to try and attempt to write the perfect prompt, but we are actually going to try and attempt to write the perfect test. Cool. So we have a contract, we have a module to implement it, we have some data and a way to evaluate whether the module is doing good or doing bad. Now we can just choose an optimizer. There are several optimizers. We can just choose an optimizer and compile our module. And then we can run that new module against the same data and see if it's good enough. If it's not good enough, we can change the module. Like I said, go for a more complex version of the module. The data will remain the same, run the compiler again, and that's pretty much it. If you have new updates, like if you have a new model, just run compile again. Like you don't even have to do anything. If you have a new module, you already have the data, you already have the evaluation set, so just run the compiler again. It will figure out the best instructions for the new model. And if you have some new use cases, all you need to do is update your sample data or your examples, or maybe even update the evaluation set if you think that needs to be changed, and run the compiler again. How simple is that? So this is true freedom. Your application logic, like the signature part, becomes stable. It's a fixed contract which doesn't change even if your module or your models are changing, right? The prompt becomes a temporary output artifact which the system is going to figure out for you, right? So it's almost like the new binary of LLM applications. Okay, I think that's enough of talking. We need to look at some code now. All right, so this is a sample naive program in DSPy just so that we can get used to the syntax a little bit better. Think of it as the hello world, right? So in DSPy, things are very standard. I think you'll feel right at home. The first step we do is define our language model, right? We define our model. Here I'm using Gemma 3. And yeah, don't get confused. OpenAI doesn't host Gemma 3. It's just that I'm using an OpenAI compatible server and I've overridden the base URL and the API key so that I can use my own server. That's pretty much it, right? Don't get confused here. We're always going to use open source model, guys. Open source for the win. Okay, cool. So we have a model. And remember what was the first step we need to do? We need to define a signature. And a signature is a declarative contract. So what is included in a contract? It's question. The input is going to be a question, which is string. The output is going to be a response, which is also a string. But a signature also includes some fundamental instructions. For example, answer the question in the voice of Pikachu. It's my stream. We had to include Pikachu somehow. Pikachu has to be there, okay? It's a rule. Okay, so the DSPy team acknowledges that you cannot completely eliminate the act of writing prompts. For example, how on earth would the module come to know that it's supposed to answer in the voice of Pikachu? There is no way it could just learn it itself. Even if it could, it would be a very costly and expensive exercise. So sometimes, as a signature creator, it just makes sense that, you know what? This is a fundamental aspect of the prompt. So I'm just going to write it up front. So that is included in the signature. Again, remember, you don't want to exploit this. You don't want to start writing things like think step by step. You don't want to use any prompting technique. You just want to put your fundamental instructions in. That's it. And in my case, it's answer in the voice of Pikachu. That's pretty much it. The rest, we'll trust that the compiler will figure out for us. Now, okay, we have a signature. So now we need a strategy to implement this contract, right? And the most simplest module we can use is called the predict. It's just an LLM call, right? It's just taking the user's question and just going to give it to the LLM and get back the answer. It's pretty straightforward. And once you have a module, you can simply call it. It's a callable. And you can give it a question. Because my input was a question, I'm going to give it a question arg with what's the meaning of life. So Pikachu, can you let us know what is the meaning of life? There we go. That's the answer. Oh, actually, I should do inspect history as well. Just give me a second, guys. Okay, so let's run it again. Pikachu, what is the meaning of life? And there we go. Cool, so this is the answer. Whatever, who cares? Ooh, that's what makes life sparkle. Okay, that's cute. So this is the prompt which actually went. So this is the predict module in action, right? So the first thing it did in the system message was it's just trying to define the contract, right? Like, hey, the input field is a question, the output field is a response, right? All interactions will be structured in the following way. So just defining the structure of what the messages are going to look like. It needs to end with completed, blah, blah, blah. And that little instruction that we had, it just added it here, answer in the voice of Pikachu. Now, this is kind of long. I'm not going to lie. It is kind of long. Smaller models kind of trip up because of this, but it's fine. You know, I can live with it. The next thing we have is our user message. That's where the question comes in. So what's the meaning of life is the question. And it's also just reiterating on what the structure should be. And what did the model respond with? It gave us the response, meaning of life, completed. And that's what the underlying adapter just parsed out for us. Sweet. That works. Now, let's say that this wasn't good enough for whatever reason. Let's say we ran the optimizer and we were like, okay, this is not good enough. But, you know, I'm just going to cheat now because I just want to show you something cool. I can change the implementation strategy without changing the contract. So the way I give the input and the way the output looks, like remember here, in the output, we got a response arg back. The way we get the input and the way we get the output will remain the same, but we just change the implementation strategy. So what is chain of thought? You know what? I'm not going to explain it. I'm just going to run it. So something different happened here. So chain of thought is just a thin wrapper on top of the predict module. And what it essentially does is it includes an additional output field by default. So instead of just response, now we have a reasoning field as well. This was added by the chain of thought. This is not there in our original signature. Chain of thought modified the signature, it's added the field reasoning. And now because reasoning is part of the response field, the model is actually thinking before answering. Now, this is a very meaningless example. I know. Okay, Pikachu. Yeah, I just had to have some fun, okay? I'm just a boy. Let me have my fun. But the point is, you see, new input fields got added, but the output is still in response. But yeah, now you have an additional reasoning field, which you could use as well if you want. Now, this module could have been making 10 calls under the hood, 30 calls under the hood. It really doesn't matter. The strategy can change. Your signature remains the same. That's the beauty of DSPy. Okay, now that we know the basic syntax, I think it's time to look at some actual code. Like how would our intent classifier look in DSPy? All right, sweet. So this is our intent classifier equivalent in DSPy. Again, we configure our model first. That's the same. Now this is a slightly different way of creating signatures. So whenever you have a signature which is slightly complex, like in our case, we want some kind of enum, right? So you write it like this. You can create a class which extends DSPy signature. The doc string here becomes that instruction you wanted to add. So identify user's intended action based on the given query. That's like the extra instruction we wanted to add. Again, keep this crisp. You don't want to overdo it. And what I'm doing here is we can use pedantic models to define all our schema, but we have simple types. So we're just doing, hey, we have a string query, which is the input field. And we have an action, which can be one of this. So it's kind of like an enum, which is the output field. It's exactly the same, just a slightly different way of defining the signature. And here I'm just going for a chain of thought again, because I know I'll need chain of thought. I've already done this exercise before. I won't bother you with it. And then I can just make the prediction and get the output. It's just straightforward. So this is just how we write the program, and I can run this. The base query that DSPy creates is usually not the best. So it's most likely going to mess up. I would never really use the base DSPy version without optimization because it makes no sense. But yeah, it definitely messed up. I bought my groceries is get task. Like it's really, really bad. But we still need a baseline, right? We still need to know like how bad is the module or how good is the module. And that's where evaluations comes in. Remember, evaluation is a first class concept in DSPy. You have to do it no matter what. So configure another module. Now I have to include this cache equals to false because by default, DSPy will cache every request. So I just want to make it false so that whenever we're running the evaluation, we are doing fresh calls and we're not just using cache responses. Ignore this part. This is the example dataset which I was talking about. So we create a DSPy.example object and it's going to have the same keys as you had in your signature, right? The input is query. So here's the query. So give me today's list of tasks and the expected action would be get tasks. Similarly, I bought my groceries. Oh, it shouldn't have been here. This is like polluted. That's fine. I bought my groceries and the action should be mark task as done. I don't need to buy groceries. The action should be delete task. This is the evaluation set, or as DSPy calls it, it's the def set. But this is how you'll test whether the module is doing well or not. So you really want these examples to be representative of what your actual query distribution is, right? Yes, it requires some work. I know it does, but it can be very easily automated once you have a good observability system in place. Cool. So I'm just marking the input separately because in examples, there's no easy way to mark input. So I'm just saying that, hey, query was the input. The rest by default is output. And then remember, we have the examples. The next step was metric, like the evaluation function, which is actually fairly straightforward. We have an example and we have a prediction. This comes from the module. This comes from our example. And then we just check whether the action is the same or not. And because this is just a Python function, you could do anything you want in here. You could do a static match like what I've done here. Or you could actually use another DSPy module or an LLM call, like an LLM as a judge, to figure out if the answer is good subjectively or not. For example, in RAG, if you want to make sure that the answer contains these 3 points, you can use an LLM to just figure those nuances out for yourself. So it's very flexible. You can have any kind of metric. It's super powerful. And then DSPy also gives you like an evaluator function, which, just runs the evaluation for you in an easy way. You don't have to use it. You could just write a for loop and do it yourself. I'm just using it because I'm lazy. So let's run the evaluator so we get the baseline performance of our newly created intent classifier module. It's going to take some time. Let it run. Cool. So we're getting roughly 60%. So our rough baseline performance is 60%. Okay, so we definitely need to improve on this. But now because we have a metric, right? Because we know we have a way to say whether something is right or wrong. Oh, by the way, the metric doesn't just have to be true or false. It could even be like a float number. So it could be a float number or true or false. I think it should be between 0 to 1. I'm not sure. Read the docs, confirm it. Since we already have a metric, what we can do is we can start optimizing our modules. We can let DSPy figure out the best prompts for us. Now, this is the DSPy optimizer code. So you see, I have another train set here. Now, this train set will not have the same examples as your eval set. You want to keep them separate, right? You can do a random split. There are a lot of ways to create your train set from your total example database, but just make sure that, this follows the same distribution as real data, okay? You don't want this to be skewed in one direction. That would not be nice. And remember, our module is actually chain of thought and it actually has reasoning. So in some places, I've actually even supplied reasoning to train the model on how to reason, You have to be very careful when you're doing these kind of things. I'm confident with what I'm doing, so I'm fine with that. But yeah, train set should not be the same as the eval set. They should be different. And both of them should be indicative of your real production queries. So we mark the input query as the input. And we have the same metric right here. And this is how we optimize or we configure the optimizer. It's fairly straightforward. So the optimizer we are going to be using today is Bootstrap few shots with random search. What it essentially does is it uses a prompting technique called few shots. For anybody who doesn't know what few shots is, we'll get to it in a second. But the idea is essentially you're going to give the model some examples of how to solve similar queries. So when it gets a new query, it has some examples to go off of, and potentially it helps improve the quality of the results, right? We'll actually see if it does. We're not going to actually add instructions. We're just going to give it some examples in its context window so that it can try to solve novel questions better. Hopefully, that's the idea. So Bootstrap demos is that this module will try to create its own examples. It will use 5 of my examples. Because we have a big data set, it's going to make 10 candidates. So it's going to run this 10 times and see which examples give us the best result. So it's like statistical, and it's just going to run it on 4 threads. And that's it. That's actually pretty straightforward. Every optimizer will have its own quirks. You don't have to worry about it. And what you get back from the optimizer is a new program. So we gave the original program in and we got a new program in, which is just the module. It's just the compiled form of the module. And the only thing different between the optimized program and the original input program, or the input module and the optimized module, is a state file. That's literally the only difference. We'll talk about that also in just a second. But the idea is some state file gets generated, which is some JSON file. And that's pretty much all we need to optimize a module again without running the whole optimizer again. We'll get to it in a second. So, okay, let's run the optimizer. Now, this is going to run really quick because I've cached everything. I don't want to run it. It takes quite a lot of time. But what it essentially did was it was randomly selecting some shots and they were running it against the training set. And I was seeing whether, when I select these set of examples, I get 50%. If I set a different set of examples, I get 83%. And it does that 10 times. And then eventually it gets this. What shots give us the best kind of output? So we have quite a few 83%, it seems like. So it's going to use one of them. So the best score is 83. So it's going to use those shots, right? Okay, let's just run the evaluation again. Again, notice I am not changing my evaluation code at all. I'm not doing that, hey, use this optimizer code or something like that. I'm not changing the evaluation code at all. It's the same code. We're not even going to open that file, but let's just run it again. Cool. I think I saw 75% there. From 60 to 75. Not bad. Not bad at all. Especially that when you consider that I'm not really using a 12 billion parameter model. I was fooling all this while. We are using a 4 billion parameter model. So if I had to change the model to 12 billion and run it again, we get 100% success rate. And remember, 12 billion was the exact thing we were struggling with when we were prompting it ourselves, right? So it just works. Ideally, I should have optimized when I changed the module, but Gemma, it's the same family, so I don't really bother. But if the module changes, you could run the same optimizer again. The optimizer would figure out the best examples to use for that model. Like these examples work for Gemma, might not necessarily work for another model. The optimizer takes care of those nuances. So we're getting a perfect result now without writing any prompts ourselves. So what I'm going to do is I'm going to show you the new prompt which just got created by the optimizer. So what did the optimizer actually do? Let's just have a look at that. That's a big prompt. So you'll notice that the system message is still the same. There's nothing fancy going on here. We have still the query as the input. We have actions, and the action is one of these 5. So it's still the same, nothing fancy. And because we're using chain of thought, it injected this reasoning thing. And then we're also showing the structure that, okay, query is supposed to be like that, reasoning, action, blah, blah, blah. And this is the little extra instruction that we had put in. But now the question that, we are messing around with was, I have bought my groceries. That's what we are actually seeing the prompt for right now. But what's actually happening here is that DSPy changed the prompt which is going out. Instead of just giving the question directly, it's saying, hey, this is an example of the task, though some input or output fields are not supplied. So if the query was delete the task about doing the dishes, the answer should be delete task. So it's kind of making a conversation. Like this is a message array which is going to the LLM, right? Instead of giving the question directly, it's giving some examples. Now, this is one way to do it. Like DSPy is choosing to put it in user assistant. There are ways you can configure to put everything in the system prompt directly and, make it more concise. You can do all of those crazy things. You can literally change the way all of this information is presented to the model by using something called adapters. We won't get into adapters today. That's a topic for a future video. But the idea is the default adapter with the default optimizer is giving us samples or some examples rather in the input. Like if this was the query, this should be the output. If this was the query, this should be the output, so on and so forth. And then eventually it gives the actual query and the model gives us a better answer. This is the few shot prompting technique in example. That's exactly what few shots is, right? The question is, when running that evaluation, we did not really change any code. So how did our old module, which was unoptimized, right? We saw it do poorly. How did that suddenly become good? The beauty of the way modules work and this abstraction these guys have created is that, one second, let me open the right file first. You see this one line? So when I have my module, I'm actually checking if this JSON file that we are outputting in the optimizer, what I'm doing here is that I'm seeing if that file exists, and if it exists, I'm just loading it up. So the optimizer result is actually just a JSON file. That's literally all it is. So if I go back and check out the JSON file, you see these were the demos of the few shots. Like the first one is I don't need to buy a water bottle. That's delete task. Delete the task about doing the dishes. That's delete task. I cleaned up my house, that's mark task as done. So and it doesn't matter what module you're using, even if you're using like an agent, even if you're using some kind of a complicated LLM workflow or using custom modules, all optimization does is just a JSON file, which means you can load them up, version control them, have multiple optimization files, one for each model that you have being used, and it just works. That is so powerful. And the best part is that we did not spend any time trying to figure out what are the perfect instructions or what should we do in order to make this work. We just ran the optimizer, spent a few cents, and got a perfect result. That's a massive win. So clearly this programmatic approach and this DSPy way of optimizing is really powerful, right? It's going to save you a ton of time. You don't have to like prompt engineer manually ever again. But you guys are smart. You guys are builders. And I'm sure you're going to find some blind spot here. I'm fairly new to DSPy, so I want to hear from you. What's an edge case or some kind of a problem that you see coming in when you're using this compiler driven method of LLM development? I'm really curious to know your thoughts. Just drop in a comment and let me know what apprehensions you might have. Oh, and also, this is the most basic DSPy program ever written. We're going to actually see how we can make workflows in DSPy and optimize entire workflows from scratch. So probably a good time to subscribe because that's the topic for the next video. So just to quickly summarize, all we need to do is if we have a new model, we go to our optimizer file, we update the model we have here, and we simply just run the optimizer again, save the JSON file, and use that in our program. That's it. And since we have an evaluation set running as well, we'll know whether the new optimized program is doing good. If we have a new use case or the use case changes, just add another example in the train set, right? And in the eval set as well. So for evaluation and for training, and the optimizer will do its magic again. This is the most basic optimizer out there. There are much more powerful optimizers which can actually write instructions for you. Yeah, that's DSPy. You can do all of this without changing any code. All you're doing is playing around with some examples. And that to me is just magic. And the fact that I can change models as new models come in, not worry about prompting techniques at all, and how future-proof my application becomes, that's really good. I know this looks powerful, but there are going to be some questions. So let me address some which I originally had. So the first question was the prompt instructions that an advanced optimizers would create. What if it's worse than an example written by hand? That's a valid question. And I'm not going to argue that DSPy can write better instructions. I don't know that. I haven't played around with it enough to claim either way. But what I'm going to argue is the fact that I save so much time and that I have a fixed signature now, and all I need to do is just add new examples or change the model and just run compile again or run optimize again. That saves me so many hours. And it's a very reproducible and consistent and a reliable way to do things. So even if we can't squeeze out like every ounce of performance from a model, I think the time we're going to save and the developer velocity that we're going to get out of this, that's worth it. That's more important than prompt perfection for me. You can spend those 10 hours worrying about new features and shipping features. That's what engineers do. Now, the second question somebody may have is the optimization we ran, that seems expensive. And in fact, even the final prompt which gets created is so verbose, or we're spending so much cost in optimizing, and we're also probably going to be spending more money in running the model. I'd actually argue that DSPy is cheaper. Why? Because first of all, you're saving a lot of developer time. Optimizing is just going to cost you a few dollars. You would spend 2-3 hours. So what's your time worth, right? Moreover, DSPy is going to give you the freedom that as a new model comes in, you can switch to it without worrying at all. Obviously, You have your eval sets to make sure that the new model still performs, but your optimizer will create new prompts for that model. That means the way this industry is advancing and the way the models are constantly getting cheaper, you might be using some extra tokens in your prompt, but you're using a model which is like half the price. Like that's exactly what happened with Gemini drop, right? It just killed the market. So the fact that you can use newer models as they arrive, or you can use newer prompting techniques in the future, which might, consume less tokens, that flexibility and future proofing is more important. And I think will save more money down the line, even if it means that you're spending a little bit more money because your prompts are slightly bigger. So the question about the perfect prompt or the cost, it's not something I would worry too much about. I think DSPy just trumps all of that. All right, I think that's all I have to share with you guys today. So if you are a builder and you want to build more resilient apps which are future-proof, make sure you subscribe to this YouTube channel because trust me, we are just getting started with this DSPy journey. There's so much more planned. We want to build workflows with DSPy. We want to build agents with DSPy. We want to do all of those crazy things. Yeah, the takeaway is simple. Stop being a prompt fiddler. I mean, let's start being AI engineers. We need to stop fiddling. We need to start compiling. So don't forget to like, share, and subscribe if you found this video to be helpful. And don't forget, I am your tech bud here on YouTube and hopefully in real life.